When calculating feeders and subfeeders, the National Electrical Code, specifically Article 310.15b16, dictates whether an 80% continuous duty duration factor needs to be applied to the conductor ampacity. This factor comes into play when dealing with loads that are considered continuous. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. If the feeder or subfeeder supplies a continuous load, the conductors must be derated to 80% of their ampacity, or conversely, the overcurrent protection device must be rated at no less than 125% of the continuous load. Now, let's address the specific scenario of a transfer switch. Generally, a transfer switch is not classified as a continuous load. This is because a transfer switch is unlikely to be actively transferring power and carrying its full load for extended periods of 3 hours or more. Consequently, the 80% continuous duty duration factor typically does not apply to the conductors feeding a transfer switch, unless it is known that the transfer switch will be carrying a continuous load. Now, to clarify the conductor sizing in your particular case, you have a 400 amp transfer switch with 500 kc XHHW-2 TC feeders. According to Table 310.16, the permitted ampacity for 500 kc XHHW-2 conductors is 380 amps, assuming the typical conditions of not more than 3 current carrying conductors in a raceway, cable, or earth, and an ambient temperature of 30 degrees Celsius. Now, if you were to apply the 80% continuous duty duration factor, the allowable ampacity of the 500 kc conductors would drop to 304 amps, calculated by multiplying 380 amps by 0.8. Considering the next size-up rule outlined in Section 240.4b of the NEC, which permits you to go to the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard breaker size, the next higher standard breaker size above 304 amps is 350 amps. This is where the question of terminating 500 kc XHHW-2 conductors on a 400 amp breaker arises. If the 80% duration factor is not applicable, the 500 kc conductors with an ampacity of 380 amps are suitable for use with a 400 amp breaker, as long as other derating factors for ambient temperature or the number of conductors in a raceway do not further reduce the conductor ampacity below the breaker rating. However, if the 80% duration factor is required, the 500 kc conductors, now effectively rated at 304 amps, are no longer appropriately sized for a 400 amp breaker. In this case, the next size up rule would allow you to use a 350 amp breaker, but not a 400 amp breaker. It is important to note that the NEC does not require you to use the next size up breaker. It only permits it under specific conditions. In situations where the calculated load is close to the conductor ampacity, it is generally better practice to select a conductor size that meets or exceeds the load requirements without relying on the next size up rule. To summarize, the legality of terminating 500 kc XHHW-2 conductors on a 400 amp breaker depends on whether the 80% continuous duty duration factor applies. If it does not apply, the conductors are suitable. If it does apply, the conductors are undersized, and you would need to use a small breaker or increase the conductor size. In the specific scenario, where the 80% continuous duty duration factor must be applied, it is correct that you cannot terminate 500 kc XHHW-2 conductors on a 400 amp breaker. In this case, one would either have to use the next smaller size breaker at 350 amps, or upsize the conductors to compensate. The appropriate conductor size, in this case, would be 350 kc XHHW-2. To clarify further, let's delve into the nuances of conductor ampacity and derating factors as they relate to feeder and subfeeder calculations. The National Electrical Code provides a framework for ensuring the safe and reliable distribution of electrical power. A key component of this framework is the proper sizing of conductors. Conductor sizing involves selecting conductors with an ampacity, which is the current carrying capacity, sufficient to handle the expected load. The ampacity of a conductor is influenced by several factors, including the conductor material, size, insulation type, and insulation conditions. Table 310.16 in the NEC provides ampacity values for various types of conductors under specific conditions. These conditions include an ambient temperature of 30 degrees Celsius and no more than 3 current carrying conductors in a raceway or cable. However, these values are subject to deration factors, which are adjustments to the ampacity to account for conditions that reduce the conductor's ability to dissipate heat. Deration factors are applied for ambient temperatures above 30 degrees Celsius for more than 3 current carrying conductors in a raceway or cable, and for other specific conditions outlined in the NEC. The continuous load deration factor, which is the 80% factor we've been discussing, is another crucial consideration. As previously mentioned, this factor applies when the load is expected to operate at its maximum current for 3 hours or more. The NEC defines a continuous load in Article 100 as a load where the maximum current is expected to continue for 3 hours or more. The 80% deration factor is applied to the conductor ampacity before any other deration factors are considered. It is important to note that the 80% deration factor is not a safety factor. It is a correction factor that accounts for the increased heating of conductors when they are subjected to continuous loads. Without this deration factor, the conductors could overheat, potentially leading to insulation damage and, in extreme cases, fire. In the context of feeder and subfeeder calculations, the first step is to determine the total load that the feeder or subfeeder will be supplying. This includes both continuous and non-continuous loads. For continuous loads, the current is multiplied by 1.25, which is the inverse of 0.8, to account for the 80% deration factor. The total load is then used to determine the minimum required ampacity of the feeder or subfeeder conductors. Once the minimum ampacity is determined, the appropriate conductor size is selected from Table 310.16, taking into account any applicable deration factors for ambient temperature, number of conductors, and other conditions. It is crucial to perform these calculations accurately to ensure that the conductors are adequately sized to handle the expected load. Now let's consider some additional factors that can affect conductor sizing. Voltage drop is an important consideration, especially for long feeders or subfeeders. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% overall, including both feeders and branch circuits. To minimize voltage drop, it may be necessary to increase the conductor size beyond what is required for ampacity. Another factor to consider is the type of load being supplied. Some loads, such as motors, can draw a large inrush current when they start. This inrush current can be several times the normal operating current. The NEC provides specific rules for sizing conductors for motor loads to account for the inrush current. In addition to the NEC, other codes and standards may apply to electrical installations depending on the location and type of occupancy. These codes and standards may have additional requirements for conductor sizing. It is important to be familiar with all applicable codes and standards before designing and installing an electrical system. In summary, proper conductor sizing is essential for the safe and reliable operation of electrical systems. The NEC provides a comprehensive framework for conductor sizing, but it is important to understand the underlying principles and to apply the rules correctly. By carefully considering all applicable factors, including ampacity, deration, voltage drop, and load type, it is possible to select conductors that are adequately sized to handle the expected load and to ensure the safety of the electrical system. Now, to further elaborate on the concept of the next size-up rule, as stipulated in Section 240.4b of the National Electrical Code, it's essential to grasp the precise circumstances under which this rule can be applied. This rule is not a blanket provision allowing for the automatic selection of the next largest standard over current device. Rather, it is a conditional allowance intended to address situations where the calculated conductor ampacity does not precisely align with a standard over current protection device rating. The NEC outlines specific standard ampere ratings for overcurrent devices, such as fuses and circuit breakers. These standard ratings are listed in Section 240.6a. When the calculated conductor ampacity falls between two standard ratings, section 240.4b permits the use of the next highest standard rating provided that certain conditions are met. Firstly, the conductors being protected must not be part of a multi-outlet branch circuit supplying receptacles for cord and plug connected portable loads. Secondly, the ampacity of the conductors must not be less than the rating of the overcurrent device where the overcurrent protection is provided for motor branch circuit conductors. Thirdly, the next higher standard rating selected must not exceed 800 amps. If the calculated conductor ampacity is greater than 800 amps, the next higher standard rating is permitted only if the calculated ampacity is not a standard rating listed in section 240.6a. It's crucial to recognize that the next size up rule is an exception to the general rule that conductors must be protected at their ampacity. Therefore, it should be applied judiciously and only when the specific conditions outlined in section 240.4b are met. Misapplication of this rule can lead to undersized conductors being protected by oversized overcurrent devices, potentially creating a fire hazard. In scenarios where the calculated conductor ampacity is only slightly below the next highest standard overcurrent device rating, it may be prudent to upsize the conductors to match the overcurrent device rating rather than relying on the next size up rule. This approach provides a greater margin of safety and ensures that the conductors are adequately protected. For example, if the calculated conductor ampacity is 195 amps, the next higher standard overcurrent device rating is 200 amps. In this case, it would be preferable to use conductors with an ampacity of at least 200 amps, rather than relying on the next size up rule to use a 200 amp overcurrent device with 195 amp conductors. Furthermore, it's important to consider the cumulative effect of multiple derating factors when applying the next size up rule. If the conductor ampacity is reduced by derating factors for ambient temperature, number of conductors, or other conditions, the next size up rule should be applied to the derated ampacity, not the original ampacity. In summary, the next size up rule is a useful tool for addressing situations where the calculated conductor ampacity does not precisely align with the standard overcurrent device rating. However, it should be applied cautiously and only when the specific conditions outlined in section 240.4b are met. It's important to prioritize conductor safety and to avoid oversizing overcurrent devices, which can compromise the protection of the electrical system. Now let us discuss the application of the 80% rule when dealing with electric vehicle supply equipment, also known as EVs. Electric vehicle charging is becoming increasingly prevalent, and it's crucial to understand how the 80% rule applies to the conductors and overcurrent protection devices that supply EVs. The NEC provides specific guidance on the installation of EVs in Article 625. According to Section 625.41, the branch circuit supplying EVs must have an ampacity not less than 125% of the maximum current of the equipment. This requirement is essentially the same as the 80% rule, as 125% is the inverse of 80%. The reason for this requirement is that EVs is often considered a continuous load, as it may operate at its maximum current for extended periods of time while charging an electric vehicle. Therefore, the conductors and overcurrent protection devices supplying EVs must be sized to account for the continuous nature of the load. It's important to note that the 125% requirement applies to the maximum current of the EVs, not the rating of the electric vehicle charger itself. The maximum current of the EVs is the current that the equipment is designed to deliver to the electric vehicle. This information is typically found in the EVs nameplate. For example, if an EVs has a maximum current of 40 amps, the branch circuit supplying the EVs must have an ampacity of at least 50 amps, calculated as 40 amps multiplied by 1.25. In addition to the 125% requirement, other derating factors may also apply to the conductors supplying EVs. These derating factors may be for ambient temperature, number of conductors in the raceway, or other conditions. It's important to consider all applicable derating factors when sizing the conductors to ensure that they are adequately protected. The overcurrent protection device supplying EVs must also be sized according to the 125% requirement. The overcurrent protection device must have a rating not less than 125% of the maximum current of the EVs. However, the overcurrent protection device must also comply with the requirements of Section 240.4, which may allow for the use of the next size up rule in certain circumstances. In summary, the 80% rule applies to conductors and overcurrent protection devices supplying EVs, as EVs is often considered a continuous load. The branch circuit supplying EVs must have an ampacity not less than 125% of the maximum current of the equipment, and the overcurrent protection device must have a rating not less than 125% of the maximum current of the equipment, subject to the requirements of Section 240.4. It's important to consult Article 625 of the NEC for specific guidance on the installation of EVs, and consider local and state amendments to the NEC which may supersede or add requirements.